Hello and welcome to lesson 5.3, limits. So today what we're going to do is we're going to talk about what a limit is, how we can calculate it, and why is it useful. So a limit is a value, let's call it L, that a function f of x gets close to as the independent variable approaches a specific value. Let's say as x approaches a. So to determine a limit, it's often necessary to actually work out what's called the left-handed limit and work out the right-handed limit. So the left-handed limit is usually listed as LIM for limit. X approaches the value a, so a is a real number, and we usually put a little negative sign almost as an exponent on that a. We place our function, and then we get our value. So L is supposed to be a value. Likewise, on the right-handed side, we do limit. As x approaches a, we put a plus sign instead as an exponent. F of x equals L. Now you may have seen these same symbols or same notation, or part of this notation, used when we talked about end behavior in grade 11. And we did revisit it here in grade 12. So, similar notation. So a limit is said to exist if this limit, as x approaches a from the left, equals this value L, and so does the limit as x approaches a from the right. As long as these two are equal to each other and equal to the same number, then the limit is said to exist. If this doesn't actually happen, or if one of these don't work out, the limit is said to not exist, or does not exist, and sometimes may be referred to as DNE, short form for does not exist. Okay, so let's see how this works out. So here I have a piecewise function, f of x. You can see is made up of a quadratic, a point, and a line. So as we approach the value of -2, we're approaching it along by traveling along this quadratic. Excuse me. And as you get closer and closer to the value of 2, the y value you get infinitely close to is actually 3. So you just say is equal to 3. Not approximately, equal to 3. Likewise, as you travel along the line, as you get infinitely closer to the value of 2, you'll notice the y value gets really, really close to 1. So just based on these two values right here, as these two values do exist, but they don't turn out to be the same number, this limit is said to does not exist. Even though the point at 2 actually equals -1. That actually turns out to be besides the point. It doesn't matter what that is. Okay, so let's see another instance. Here I have another function, f of x. Looks like a line with a hole in it, or there is also the possibility that this could be a rational function. So, as you approach from the left, you're getting infinitely closer to a y value of -1. As you approach from the right to the value of 2, you get infinitely closer to a y value of -1. Since these two values are exactly the same number and they're approaching from the left and the right, you say this limit does exist and also equals -1. Even though at this point you have a hole. Even though the value does not exist. So f at 2 does not exist, or is also called undefined. That's, again, besides the point. The limit only looks as it approaches from the left and from the right infinitely closer. We'll talk more about what happens when you do have these kinds of holes. Okay, so based on this, we can come up with some kind of limit properties. First, notice we do have values of c, a, and n throughout these expressions. These are real numbers. And f of x and g of x are just functions. Does not matter what type of function, technically. These are just actually functions. So the first two limit properties help us out. So the first limit property, I'm going to draw a constant function, y equals c in this case. As you approach the value a from both sides, you'll notice that that y value still remains c, no matter what, on both sides. So the limit exists and is equal to c. In limit property number 2, you can just look at the line y equals x, which is just a diagonal line, the slope of 1, at the value a. As you approach from the left and the right, you get a y value equal to a. So it does turn out to be the exact same value. The rest of the limit properties, numbers 3, 4, 5, 6, and 7, are just combinations of this. So limit property number 3, you can actually join up a linear and a constant function into one just by using addition or subtraction. You can even multiply your function by a constant. You can even take two functions and multiply them, and you get the same limit. You can even divide them and get the same limit. Or you can even apply it to an exponent and get the same limit. So what this leads us to is another hidden limit property. We're going to call it number 8, which is called direct substitution. With this direct substitution, all you have to do is substitute a value in to your function. If it exists, then the limit does exist. If the limit turns out to be something different, which we'll see in a second, it's gonna be undetermined, and then we'll figure it out later on. But if it does exist at a value, then it works out. So let me show you when it does, when it doesn't, and what options we have when we're not sure. So we're going to determine if the limit exists for these two functions. So first off, first limit, just try substituting 1 in. Well, here you can actually substitute it in and get the value 7. So the limit does exist as you approach the value 1, and it is equal to 7. Whereas if you substitute 2 into our second equation, so 3 minus 2 times 2, you'll notice we get a square root of -1. As we're dealing with real numbers here, the square root of -1 doesn't actually exist. So since that doesn't exist, this limit does not exist. Okay, so what happens for other types? Well, if ever the limit turns out to be having a problem with direct substitution, we're going to see something interesting happen here. So here we're going to try direct substitution, and we're going to see something different happen. So when I substitute 3 in, I get 25 minus 3 plus 2 squared all over 3 minus 3. Well, this gives me 0 in the numerator and 0 in the denominator. This creates a hole. When this happens, this is called indeterminate. meaning we do not know actually what the value is. Only when we get it does not exist or a value actually come out of it do we actually tell what it is. So with these ones, try some other options. Try to factor, try to expand, try to cancel some things. It may work out. So for this one, what we're going to try is, notice that 25 and the x plus 2 squared is a difference of squares. So I'm going to change this into the limit as x approaches 3 of 5 minus x plus 2 and 5 plus x plus 2. Okay, so our first expression actually turns out to be 3 minus x, and the second expression turns out to be x plus 7. Well, there you might notice that the 3 minus x and the x minus 3 can cancel out. So I'm going to cancel that out. And again, we don't actually care what's happening at the value. We only care what's happening close to the value. And that's why we can cancel these things out without causing any problem. So now that I canceled it out, I've got to multiply by a -1 when I cancel that out. So this, I can substitute the value 3 in without an issue, and I get a limit as -10. So again, let's try this next one. Let's try direct substitution. If I substitute the value 0 in, I get 0 minus 0 over 0, which is 0 over 0. So that doesn't work. Let's try again to factor. So I can factor out an x from the numerator. I can cancel one of the x's from the numerator with one of the ones from the denominator. Now if I do try direct substitution now, I get 0 minus 3 over 0. Because the top number is a number, -3, the bottom one turns out to be 0, this does not exist. Okay, let's try some others. These ones are a little bit more challenging to deal with. Because of the square roots, again, if you try direct substitution, it's not going to work out. So with direct substitution, just to show you, you do get 0 over 0, and you get 0 divided by 0 in this case as well. So again, you need to try some other things. With these ones, we saw how to deal with square roots before. We call it rationalizing the denominator. So what we're going to do is we're going to use the same kind of strategy to help us out here. Okay, so for this one, I'm going to multiply the top and the bottom by the same value. This time I'm going to multiply by 1 plus the square root of x plus 3. It's the same expression that I had in the denominator, except for in the middle between the one function and the other function, I'm changing the sign. When I do that, it changes the actual expression and gets rid of the square root in the denominator. If the square root's in the numerator, that's causing the problem, then try to get rid of it there. So when you expand it, just try to expand the one that is causing the problem. or the one that you're trying to get rid of the square root. So in the numerator, I'm going to leave it as x plus 2 and 1 plus the square root of x plus 3. If you expand it, it may not work very nicely here. And here you expand, you get 1 minus x plus 3. So continuing to expand, you get negative x minus 2 in the denominator, which you can cancel out with part of the numerator just by getting rid of a negative. So cancel those out, put a negative in there, and your limit, as x approaches negative 2, will turn out to be equal to negative 1 times 1 plus the square root of x plus 3. Again, because you can actually get rid of your factor there, it's all right. Now you can substitute the value negative 2 into your expression and get a solution. So this limit is equal to negative 2. So let's see that again with the one on the right-hand side. For this one, we're going to multiply the numerator and denominator by the same expression that's in the numerator, just changing the sign. To see if this works out. Just because you do this does not mean it's going to work out. You're just rationalizing the numerator in this case. Okay, so if we expand, we get x plus 1 minus 1 minus x. In the numerator, denominator, we're not going to expand. I'm going to leave it as is. Now I'm going to simplify the numerator. So x plus 1 minus 1 minus x turns out to be 2x all over x. X plus 1 square rooted plus 1 minus x square rooted. So again, you'll notice that the x's cancel out in this case. And now we're looking at the limit as x approaches 0 of the value 2 over square root of x plus 1 plus square root of 1 minus x. So we can substitute 0 in. We get 2 divided by 2, which is just equal to 1. And therefore that limit does exist and equal the value of 1. So again, with all these cases, what you're trying to do is you're trying to factor, you're trying to expand using rationalization terminology if you can't use direct substitution. And thus concludes this lesson.